Okay, I couldn't resist making a few more videos to continue the story of complex numbers um, in the vein that we were doing that where we discovered this great need and a great use for them. So I want to just summarize real quick this three-part um, it's doing some weird stuff here. This three-part perspective on what's cool about the complex numbers so far. There's the algebraic aspect of it, and that's that we've got all the usual rules of arithmetic, the associative, commutative, distributive properties, things like that, plus this wonderful fact that we've invented a square root of -1. And that means we can solve, at least we can solve quadratics. And we'll see how much further we can take that. The geometric perspective, we know that there's this perspective where complex numbers can either be thought of as a point, or z, or as a vector in the plane, and adding them just corresponds to vector addition. And then multiplication is even more interesting, where you have z and w. These angles add, and you do a rotation and a scaling to get wz. And so it encodes a lot of geometry. It really encodes all of Euclidean geometry if you want to. And then the question is there further we can take that story? Then there was the analytic aspect. The calculus, that's just a fancy word for calculus, basically, or fancy calculus, let's say. So the analytic aspect, and that's really what motivated us. It turned out that we needed the algebraic and geometric aspects to be true for complex numbers in order to solve our analysis problem. We've got y equals e to the alpha t solves y prime equals alpha y, and therefore y double prime equals alpha squared y, even if that alpha squared needs to be a negative number. And this particular function happens to have a very simple initial condition, y of 0 equals 1. And this gives, if alpha equals a plus bi, then this is e to the at times cosine t plus I sine bt. I sine bt. And we get spirals. And so when we look at the real imaginary parts, we get damped or growing oscillations. And so that, of course, led to solutions to our key motivating problem, second order constant coefficient linear differential equation, and with its interpretations as vibrating spring or RLC circuit or whatever. And then so another question is, how far can we take that? What about third order equations? And I'm going to talk about other generalizations you might not immediately spring to mind, but are incredibly useful and very natural to go from there. So the reason I did the recap is I want to talk about some questions that come up, I think, fairly naturally inspired by the facts, by what we've accomplished already. So in algebra first, so algebra, my handwriting is degenerating here. Okay, so algebra, what about polynomial equations? P of x equals like an x to the n plus an minus x to the n minus 1 plus a1x plus a naught. Is there a polynomial equation, some polynomial equals 0, that doesn't have a root yet? Okay, and we could first ask the question, what if the a's are all real numbers? It's just an ordinary real polynomial, the kind of thing we would have been interested in long before we thought of inventing complex numbers. It seems very possible at this point that yes, we've got solutions to quadratics, but maybe we don't have solutions to cubics, quartics, quintics, all the higher order equations. Maybe there's some that escape us still. And, while we're inventing complex numbers, there's probably going to be good reasons to use the complex numbers as coefficients as well. So and it's very, very plausible, it seems, that when you do that, then you don't get solutions to those guys. And maybe you have to invent yet other new numbers. And maybe there's an infinite regress of newer and newer, bigger and bigger number systems that you have to do. And every time you invent new coefficients, you have to invent new places for the solutions to live. That would be unpleasant. And it can happen in other situations if you don't start with the real numbers. But wonderful, wonderful fact. And this is not going to be, I think, a surprise to most people watching this video. There's such a thing as called the fundamental theorem of algebra, which is not really purely an algebraic theorem, and I'll talk about what that means. And it says that, in fact, if you have P of z, so I'm using the z to indicate that I'm going to let the x be a complex number. That's crucial so that the solutions can be complex numbers. And you look at roots of that polynomial, and that's just a synonym for solutions to that polynomial equals 0. We want to ask if that has roots. Well, there's one case where it obviously can't have roots if it's just a constant and that constant is not equal to 0. Okay, so we're gonna assume it's a non-constant polynomial. Okay, so degree greater than 0. And if I ever forget to say that, then, and it seems like I'm saying something wrong because of that special case, it's just because I forgot to say that. If you have a non-constant polynomial looking for roots of that polynomial, then yes, it has a complex root, at least one. And then, in fact, by pretty simple algebra that has nothing to do with the novelty of complex numbers or any new number system, just division of polynomials, then in fact it's going to have n complex roots. Now, pause and think about this for a second. Think about why that's sketchy, why that seems pretty dubious. Like for a quadratic, the two roots can coincide, and you can get a double root. Okay. Well, there's a way to actually encode and determine the multiplicity of a root. When you have a root, you can actually tell when it's secretly a root doubled or tripled or whatever. And there's ways, algebraic ways, and in fact, cool calculus ways of doing that. So the nice theorem is that if we count, and this is hopefully not new to most watchers of the video, but it's not really important to what I'm saying. If we count roots with multiplicity, and I'm not going to go into exactly how to do that, then P of z has exactly n roots. In particular, it can never have more, and that's another pretty easy algebra thing to prove. Okay, and that's if this has degree n. Okay, and that's in the complex numbers, and the coefficients can be complex, and it still works. So you can solve things like z squared minus I equals 0. What are the square roots of I? What are the fourth roots of I? What are the 14th roots of I? Very interesting question, and it doesn't force you to invent new number systems. Okay, so this, in a way, is kind of amazing. That our goal was to only solve this equation. Well, we invent I squared is minus 1, so we could solve this equation, this one quadratic equation, with obviously real coefficients, 1, 0, 1, and just adding that, and then doing the incredibly natural thing of letting something have a real and imaginary part, actually gives us solutions to every non-constant polynomial. Why is that? Why don't I have to keep inventing new stuff? And it turns out to be really based on a fundamentally nice property of the reals. You might get the impression that this whole sequence of videos is kind of ragging on the real numbers and as being bad or insufficient. But what this is telling us is the reals actually are super powerful. That when you just add this one new number, then you not only solve this equation and all quadratics, which is pretty easy by the quadratic formula completing the square, you solve all possible polynomial equations. That those guys do have roots. Okay. So in the next video, I will go through a very much of a sketch of a proof, or just even a sketch of proof is a little bit optimistic for what I want to say, but just a little bit of a demonstration of why you might expect this to happen. That the real numbers really do have a wonderful property that gets you sort of halfway there, and then adding an I gets you the rest of the way to the fundamental theorem of algebra. And I think in an adjunct video, probably not in the main sequence, I'll talk about a careful proof of the fundamental theorem of algebra. There's many of them, but and I think I probably should do at least one to be honest. And that's and then I'll go on to generalizations of those other questions we had at the start.